Hello guys, welcome to my channel, and today I want us to look at density estimation using the Kernel density estimator in R, and I want us to start by considering the code. I want us to start by considering this code, the Kernel density estimator. So I want us first of all to generate random variables for normal distribution. This is how you generate random variables for normal distribution. So these are random values from a normal distribution. We are starting with size as 1,000. Sample size is 1,000. The mean is 4, and the standard deviation is 2. So the actual density will be the actual density will be generated by this code variables from the normal distribution. Mean is 4, and standard deviation is 2. Then the estimated density. The estimated density in this case will be we will use the random variables from the normal distribution as our x variable. Then the bandwidth, we are going to command R to use the UCV, which is the unbiased cross validation. Then the Kernel function, we command R to use the Gaussian. Remember, there are several others, but Gaussian is the most preferred by so many people. Gaussian, then we want to plot our estimated density together and or against the actual density and see how the two behaves. So if I run this code, yeah, this is what it gives. The black curve is the actual density from the normal random variables on normal distribution. Then the red one, you can see I have commanded R to use a red color for the estimated density. So the red one is the estimated. Let us briefly see what happens if we alter the sample size. If we change the sample size to 10, then the estimated density, you see the way it behaves. So now I want us now, remember we are interested with estimating the bias and the MSE. So let us try to now, let me adjust my code a little bit so that I can alter the sizes. So if I want a scenario where I will be adjusting my sample size there, then the variables will be generated from the size 1, which is here. Let us see how this one behaves. And that's how it behaves. So now remember, I'm interested in finding the bias and MSE. I'm interested in finding the bias and MSE. So I want us to consider these other two cons here. The bias and MSE. So how do you get the bias? You take the estimated density, you subtract the actual density. So that one will give you the bias. And the bias here is negative 0.193. Then the MSE, how do you get the mean squared error? You find the error is the estimated density, the values of the estimated density minus the values in the actual, then you square them. Remember, if you don't square the errors, the deviations from the actual ones, the total will sum to 0. So you need to square them and get the mean. So if you get the mean, then this would be the value. That will be the value. Now, to be so accurate in your interpretations, you need to repeat this function so many times so that you get the mean, bias, and mean. So for this point, at this point, I'm not interested with the plots. I'm not interested with the plots again. So I want to loop. I want to loop my function. I want to loop my function. I want to loop my function 1,000 times. I want to loop my function 1,000 times. Let me loop it up to there. Then then I loop it 1,000 times, I need to store the bias as a list. So I want to store my bias there. And I also want to store my MSE. So that if, for example, I want to see the sum of the biases, let's see what it gives. See, the sum of bias is this one. So if then I want now to get the bias itself, then I should get the mean of bias. So what is the bias? So let us check what happens. You see, so this time I have looped my program 1,000 times. Then I have computed the mean of biases. So with this value, I will be able to make more accurate conclusions later. So I'm not interested with the sum of bias. That was just to confirm that whatever I have is a mean of 1,000 values, because I have divided this one by 1,000 to get this one. I'm sure that one is now clear to you. Then the same case, I want to get MSE is the mean of these lists, the mean of these lists, so that MSE now becomes that. So because this is size 1, this is size 1, so I can call this one bias 1. I can also call this one MSE 1. You can call it even that one MSE1. So what if you are requested to find the same bias and MSE for different sizes and maybe plot? So I want to repeat the OS program. I want to repeat the O program. Now size 2, I can adjust size 1 to 10. Then size 2 to maybe 100, so that I now commanded to generate from size of 100. Then this case now I tell it to call it bias 2. Then again, I can do the same. I can do the same for size 3. Which is 500, size 3. Then I tell I command R to generate random values from a size of 500, so that now I get bias 3 and mean squared errors 3. What if I do the same for other 2 sample sizes? So I think size 4. Let me check. Size 1 is 10. Size 2 is 100. Size 3, we can call it 200. Then size 3, we can call it 500, no problem. And then this is size 4 now. Size 4 is 400, so we tell to take it from size 4, so that we have bias 4. Mean squared error 4, mean squared error 4. Then finally what if change to size 5, which is now 1,000? Then we command R to use size 5, so that we get bias number 5. Then mean squared error for the 5th scenario. So we have that. So if we run this program, it will just it should give us the biases and MSE for each scenario. But to simplify the program, I want to put this one in a table. So I want to generate a table I want to generate a table in matrix form. In this table, I have organized my output in this form: size 1, size 2, size 3, size 4, and size 5. Then the MSE, I've organized them as MS1, MS2, MS3, MSE4, MS5. Then biases, I've organized them as bias 1, bias 2, bias 3, bias 4, and bias 5. Then remember, if we want this one to be rows, then this one will be row 1, row 2, row 3, row 4, row 5, and row 6, so that the next column will have row 1, row 2, row 3. So remember to command R to use n rows, the number of rows to be 6, and the number of columns to be 3. So it will split this thing into 3 columns, each column with 6 rows. So if we request now, if we command it to print the table and run everything, let's wait and see what will happen. Wait and see what will happen. Good. So you can see it says that the matrix size 1, size 2, size 3, size 4, size 5, MSE, MS1 was not found. Bias 1, something is objective bias 1. So in this table, we have made a mistake. We have made a mistake because we are calling this one bias with double S. We're calling that one bias with double S. So let's check what will happen. Check and see what will happen. Good, 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 good. So it has printed a table of N, the sample size, the MSEs, and the biases. Now, it's a bit difficult to know what is happening to MSEs and biases by just looking at a table. So the best thing is we plot. So let us plot this thing and see what happens. I want us to rearrange. I want us to organize. I want us to organize the sample size. Those are the sample sizes, so I've reorganized. The bias, those are the biases. Bias 1, bias 2, bias 2. Then the mean squared error, those are the mean squared errors. It will, remember, R will just read. For example, if mean squared error number 1, it will just read it above. Then we want to plot sample size bias against sample size, and at the same time plot MSE against sample size. So we must put additional space for the second y-axis because these two are measured at different scales. Bias and MSE are measured at different scales, so we must put additional space for the second y-axis. That's command does that. Then we create the first plot. The first plot is the sample size is the x variable, and the mean squared error is the y variable. And we have requested, we have commanded R to use color rand for the MSE. Then we add new plot. New equals true. Then the plot is sample size is x variable, and the bias now is the y variable. Then we use lime green as the color for the line for the bias. Then remember, because we have two plots in the same graph, we need to have a legend where we want a legend to mark the bias and the MSE and tell us that the bias has got a lime green color while the MSE has the red color. So let us run this plot and see what happens. Let's run and see what this one happens. Good. And you can see both the bias and MSE behave the same. behave the same. With increasing sample size, the two tend to decrease. Both the bias and MSE tend to decrease. So let us say something is not clear here. The y and variables differ. Let us see where 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See what happens. Wait and see what happens, what the program gives. Now remember, we are running everything because it is randomly generating values, but still we have a problem with the bias. Sorry. We have a problem with the bias because I don't know why I'm using bias with I'm using a double S for the bias. And I hope every other thing is okay. So we can run everything again and wait and see what happens. See, good. And here we have the graph for the MSE is the red one, and the one for the bias is the green one. So you can try to interpret what is happening as n is increasing. As you can see, very large values for n result to very low mean squared error. In the same case, remember this bias, the biases were negatives. So as we go down, we are increasing the negative value. As we go up, we are approaching the 0. So you can see for the large sample sizes, the bias is coming closer to 0. So in short, we can see that the absolute bias decreases with increase in sample size. And I think that's all, guys, for today. We shall meet in the next video. I will also try to explain to you how you can estimate the density using histogram method. Today we were looking at the Kernel density estimator. And so we meet in the next video, guys. Remember to subscribe to my YouTube channel so that you'll be updated anytime I give you more. I will try to give you more and more so that you can understand more about this. Thank you, guys, and thank you for watching.